Test. Hello. Okay, so hello everyone. I will be substituting for Professor Kum for today's lecture. We will be covering lecture 19, which is trajectory planning for autonomous driving. And I believe this is the final lecture for motion planning for autonomous driving. So in today's lecture, I'll be covering path planning for autonomous driving, consisting of planning the composition for autonomous driving, smooth local path planning, as well as velocity policy generation. Now we'll start with planning the composition. So in general, I think everyone have learned various planning algorithms in previous lectures. And regardless of which algorithm is used for planning, or at whichever level it is used in planning, the common workflow is generally the same in robotics. So you will have a path computation, which is in a higher level planning, and then you smooth the path, and then design a trajectory. In this case, create a velocity using a velocity function to plan the velocity, and then designing a controller in order for the robot to track the trajectory that you plan. So some questions with this planning to consider is whether this planning workflow is open loop or a closed loop system. Then if it's a closed loop or open loop system, how often do you update each procedure and why? A common workflow can be displayed in this motion planner hierarchy. So you will have a high-level planner for long-range route planner. And in this case, you don't need the planner to run or at a very high frequency or to run a lot. So you can probably set it to 0.001 hertz, and that will be fine, since this only regards the route planner.
I think the monitor is being recorded.
It's not clear.
I think that's interesting.
So the next level is the short range route planner. So once you have the long range route planner, you can have a much shorter range in your planning horizon. And this may require you to run it at a higher frequency at 1 hertz, generally 1 hertz. Then for local path planner at the lowest level, you need this to be highly reactive, mainly for safety. So generally set to 100 hertz. And this is the hierarchical planning component. So generally driving missions and scenarios are complex problems. So to make them simpler, you break them into a hierarchy or simpler optimization problems. Then each optimization problem can be tailored for the correct scope and level of abstraction based on the requirements of each level. And then higher in the hierarchy means there's more abstraction. And each optimization problem will have their own constraints and objective functions suited for their level. The highest level planner is generally the mission planner. This mainly focuses on the autonomous driving mission, where you want to create the plan from point A to point B. Generally, this is also called the route planner. And this is at a this planner generally abstracts away all the lower level details and usually solved with graph-based problems. It can be solved with graph-based problems such as Dijkstra and A-star. And the next level is usually the behavioral planner. And this behavioral planner is creates decisions for the autonomous vehicle. For example, when it is safe to proceed in an intersection. So they will take in consideration of the surrounding states, such as pedestrians, vehicles, cyclists, etc. And then look at some regulatory elements, such as traffic lights or stop signs, and decide, create a decision based on that. For example, a finite state machine is one way to create a behavioral planner. So this one is composed of states and transitions. So each state is displayed here in the nodes, and transitions are also based on the inputs of the driving scenario. So you will have the states that you would like the autonomous vehicle to be in. For example, a stop, or you wanted to attract some speed, or you wanted to decelerate. And then in order to transition between these states, you will inquire about the inputs. And then once if the inputs are satisfied, the states will be transitioned from, for example, from track speed to decelerating. One property of finite state machine is that it's memoryless. So transitions only depend on the input and the current state and not on any past state sequences. Second example for behavioral planner is a rule-based system. So rule-based system usually uses a hierarchy of rules to determine the output behavior. The rules are evaluated based on logical predicates, and higher priority rules at the hierarchy level is prioritized or takes precedence. So example is in a scenario with two rules, you have if the rule states that you need there is green light and intersection, then the action that the vehicle must take is to drive straight. Or if there's pedestrian and the vehicle is driving straight, then the action that the vehicle must take is to stop, do an emergency stop. So this is another example for a more recent implementation of the reinforcement learning is for the behavioral planning. So reinforcement learning's main point is that it can learn actions through feedback from the environment. So in this case, the feedback is in the form of rewards. And the objective of reinforcement learning is to maximize these rewards, which is the total reward of a long horizon plan. Long horizon here is the planning horizon is infinite. And also the discounted plan is that it's between 0 to 1. So as you plan further into the horizon, the reward gets smaller. Then the reward is for the action at time t based on the current state as well as the next state. So once you create the result of reinforcement learning is that you should have an action that maximizes this reward in order to maximize this overall reward. For the next section is smooth local planning. So local planning generates feasible collision-free paths and comfortable velocity profiles. It is often decomposed into path planning and velocity profile generation. Local planner is for the vehicle and its immediate surroundings, and generally expressed within the frame coordinates, where you simplify where the roads are usually curved. In Cartesian coordinates, you simplify it by taking into account of the curvature and then expressing it in terms of only lateral position information and longitudinal position information. One example of local planners are sampling-based planners. So in this planner, you randomly sample control inputs in order to quickly explore the workspace. So an example of that is rapidly exploring random tree, where all these are possible trajectories that are sampled. Collision checking is performed at new points. So once you generate a point here, it will be checked for any possible collisions. And then if it's collision free, it should be added to the explored space. Can be often very fast, but generate poor quality paths because it's generally the path is not smooth and can be very rough. Another example is lattice planners. So with lattice planners, they constrain the search space by limiting actions available to the robot using a limited set of actions for the robot's control set. So in this case, for example, the lattice planner, these are the uses 3 possible control sets. So at the first iteration, here is the starting position. Then you branch out into 3 possible control states. And then at the second iteration, each branch is then branched out again into other 3 possible branches. So each layer of control action forms a graph, and then you can use graph search algorithms such as Dijkstra's or A-star for the planning. A variation of lattice planners is a conformal lattice planner, which takes into account of road structure into the control actions. Another is variational planners. So with variational planners, you optimize trajectory according to the cost function, and where it contains penalties for collision avoidance and robot dynamics. So with variational planner, this is the initial trajectory, and these points are called control points. And the goal, there's more details into this if you're interested, but the goal is that you want to move the control points based on the objective function to get to the state that you want. So this is the first iteration, and after some process, you might get this final control points, which is collision-free. Because of the iterative process, it can be quite slow, and then it's also less likely to converge to a feasible solution. For velocity profile generation, you usually take into account smoothness for smooth velocity. In this case, it's the third order derivative of x. You want to minimize this, and deviation from the reference or velocity reference, as well as limiting the velocity based on the lateral acceleration and curvature. So for variational planners, we'll cover like 4 main components, which is the parameterized paths, planning constraints, planning objectives, and optimization formulation. For parameterization, usually use parametric curves to generate the plan. So parametric curve R here can be described as a set of parameterized equations. So here, X and Y are parameterized equation, and the parameter U will denote the path traversal, also known as progress, and it can be arc length or unitless. So generally, you start with 0, and the progress is until 1. An example of parametric curve is cubic spline, formulated using cubic equations. So for parametric curve, generally, you require boundary conditions for smoothness and to find the equation of the parametric curve. So usually you use the starting and ending conditions of the path. Here, x, y, theta, and curvature kappa. some kinematic constraints include the maximum curvature, where it should not be exceeded. And this will ensure that the car can drive along the path normally. So one few things to consider is that why max curvature is an important constraint for vehicle path planning. And then in terms of vehicle design, what kind of methods can you use to increase the max curvature? And for path optimization, so the path that we generate, we usually use some cost function in order to create an optimized path. And this cost function f, generally, we want it to be minimized. And parametric curves allows us to optimize over the parameter space, which simplifies the optimization formulation. So this is a generic optimization problem where you use the parameterization of your curve. Here it's subject to constraints as well as initial and final conditions. And this is an example of the type of parametric curve that you can use. The previous cubic spline. Common parameterized curves include quantic splines as well as cubic spirals. Both allows us to satisfy boundary condition, and they can be optimized parametrically. For quintic splines, in 2D, X and Y are generally defined by fifth order splines. And here you can see that fifth order is the highest. And for this case, a closed form solution is available for X, Y, theta, and kappa, making the boundary conditions very useful. Quintic spline curvature can be challenging to constrain because of the nature of the spline definition. Because of the potential discontinuities in curvature as well as its derivatives. So this is usually the equation that we use to calculate the curvature at some point u along the progress. And since we require numerical calculations when implementing planning algorithms, we require second order derivatives and first order derivatives, which makes the curvature constraint quite challenging. Another example of parametric curve are polynomial spirals. Spirals are defined by their curvature as a function of arc length. So in this case, the cubic equation is used for the curvature instead of the X and Y position. The closed form curvature definition allows us for simple curvature constraint checking, unlike quintic splines. So curvature is well behaved between sample points as well due to polynomial formulation. For cubic spirals, boundary conditions specify starting state and required ending state. And the spiral end position lacks any closed form solution and requires numerical approximation. So the X and Y term, to get the X and Y term, you require an integration of this function, cos and sine function. And to implement it, you require numerical approximations. Usually here, again, spiral positions does not have any closed form solution. So Fresnel integrals, the integrals before, usually need to be evaluated numerically, which can be done using Simpson's rule, where you approximate the integral with the number of endpoints. So yeah, there's more on Simpson's rule. Simpson's rule has improved accuracy over other numerical integration methods, and it works by dividing the integration interval into n regions, and evaluates the function at each region boundary. Obviously, the larger n, the more accurate your integral approximation will be. So for applying Simpson's rule, here we'll take an example of using eight segments. And then we will have this form of the approximation for the x integral. And then we can also get a closed form solution for theta. And by substituting it into x and y, we can get the approximations below. Next are common planning constraints. So we use the Simpson's approximations, and now we can write out the full boundary conditions in terms of the spiral parameters. Now we can generate a spiral that satisfies boundary conditions by optimizing the spiral parameters and its length SF, which is the full arc length. And here we can formulate the earlier constraints in terms of the approximated x and y values. Another thing to note is what other kind of constraints should be considered. So you guys can consider that. For approximation of curvature constraints, we want to apply curvature constraints to the path so it is drivable by the vehicle. But and curvature constraints correspond to the minimum vehicle turning radius. So this is dependent on the vehicle design. Using the earlier spirals, we can constrain the sample points along the path due to its well-behaved nature of the spiral's curvature. So for the curvature, we can, for example, constrain it at the 1/3 or 2/3 along the way at these points, and that will be sufficient for satisfying the curvature constraint for spirals. And then we can then generate all the necessary boundary conditions as well as the constraints. For the planning objectives required, usually a common objective is efficiency, usually expressed by minimizing the path length, or in this case, the arc length of the curvature, and we minimize this. Or another way is to minimize the travel time of to the destination while following the path. So you integrate along the arc length. Sorry, excuse me. What else should be considered other than path length and travel time for efficiency? Can wonder about that. So here's an example of a path length objective. If we don't have this objective, for example, the path doesn't have any constraint to be as short as possible. And this is once we apply the objectives. And this is a curvature objective. So in this case, curvature is high. So because of the low turning radius, and that can be detrimental, or your vehicle might not be able to satisfy this this turn. They cannot use this track to turn. So ideally, you would want a smoother, low turning radius, high turning radius curvature. So another one is bending energy objective. bending energy distributes the curvature evenly along the spiral for comfort. So usually expressed by equating it to the square of the curvature equation, which has a closed form solution for spirals. The gradients also has a closed form solution, but it's best to use a symbolic solver to solve the gradients. Finally, is with the formulation of the optimization for generating the plan, the trajectory. For spiral-based path optimization problem, we can bring constraints and objective together to form the full optimization problem. So we can make things easier by performing the optimization in the vehicle's body attached frame to set starting boundary condition to 0. So now we can just set most of these to 0 to simplify the problem. Usually it is challenging for optimizers to satisfy exact constraints here, to satisfy all these constraints. One way to tackle this is to soften some of the equality constraints by penalizing deviation heavily in the objective function. So, for example, the final constraints here, terminating constraints, is now expressed as part of the objective function. So the main difference here is that you allow the plan to deviate a little bit and it will be fine. Unlike hard constraints here, you must have the trajectory profile, or the plan to finish at these terminating states. And in here, you are allowed to deviate a little bit. So you reformulate the problem into this objective function, and now you only have these constraints. Then you can further simplify the initial curvature, which corresponds to this coefficient. You can also perform parameter remapping for spirals. Here we map them into a P0 to P4, and P0 and P3, P0 to P3 corresponds to the curvature at 4 points equally spaced along the path. So here P0, P1, P2, and P3, and P4 corresponds to the arc length, and which is also correspond to the A0. Sorry, no, here SF. Sorry. A0 is P0. Then, since the initial and final curvature are known, P0 and P3 can be eliminated from the optimization problem, reducing the problem's dimensionality. Then the final optimization problem is that by replacing spiral parameters with new parameters, it will gives us this formulation. So now you only have this simple constraints as well as these soft constraints from the original optimization problem. So now the optimization problem is much more simpler. And then the curvature constraints can also corresponds directly to the new parameters. And yeah, boundary conditions are handled by the soft constraints as well as the P0 and P3 constraints. So this can be much more easier to solve. So how do you put it all together from all the different things that you learned? So for conformal lattice, again, the goal is to plan a visible collision-free path towards the goal. So conformal lattice exploits the road structure to speed up the planning. And the lattice paths are lateral offset from a goal point along the road. So to expand on that, you will first have the goal horizon, and the short look ahead which means if the goal horizon is closer to your vehicle, it improves computation time, but it also reduces your ability to avoid obstacles. But if your goal horizon is much further out, then you can take into account of more obstacles to get a much better solution. The goal point is dynamically calculated based on a lot of factors, one of them being speed. Then once you have the goal, you sample you set that as the endpoint, and then sample laterally based on the heading of along the road. So here is the goal, and you sample multiple points here based on the normal of the curve, or in this case, the road. Then we compute cubic spirals to each point. The objective of this thing, again, is to generate these path candidate set. So we have the goal offsets. Now we want to compute the cubic spirals towards each of those goal points. And at this stage, usually you only focus on the kinematic feasibility and ignore any collision checking processes. So if a goal point cannot be reached with a spiral, you can just remove it from the possible path candidates. Then you use this equation to solve these endpoints to generate the curves. And we reformulate the optimization variable, converting it into the spiral parameters again. And then we can use the spiral coefficients to sample points along the spiral. If you want to generate, if you want to find XY positions, or in this case, kappa and theta, and from there we can find the XY positions. Because of the integration here, usually we also use numerical integration to generate the positions. And another way, besides the previous Simpson's rule, is to use the trapezoidal rule integration. And this trapezoidal rule is faster for generating entire paths than the Simpson's rule. And you can create a function, a cumulative trapezoid, where you can discretize the representation generated using the trapezoidal rule integration. Here you approximate the integrals into like this form, the trapezoidal form. So now for each of our goal states, we have the curves. And now we want to optimize the spiral to our goal point. So using the trapezoidal numerical integration, we get the discrete path representations. And now from these path generated set, we want to find the paths that is collision-free. And we can do this by using, for example, circle-based or swath-based collision checking processes for each point along the path. So we use this to find all the necessary points along the path, and then check each point for any overlap with existing obstacles. So in this case here, the parked vehicle in red represents an obstacle, and the 4 curves here will intersect with the vehicle. And these paths should be removed from the generated set. So for path selection, we need to select the best path among the collision-free paths. And to determine what is the best path, we use the objective function, and this objective function is based on our design choice. For example, we can reward paths that track the center of the road or penalize paths that come too close to the obstacles. Best path is highlighted in blue by the here's an example of the selected path using the previous planning. So at each planning step, we repeat this process as the car moves along the road. So you have this curvature, but you are not expected to run the vehicle at for the entirety of this curve. What usually happens is that you generate this curve, and then you only run at one time step. Then, for example, the vehicle will be here next, and then you rerun the planner again to generate new curves. That's usually the case for the vehicle to react to the local environment. So if we use the previous objective, for example, to track the center of the road, once if the path converges from the center to avoid an obstacle, it will then converge back again towards the center once the obstacle has passed, because of our objective, since we want to reward the path that tracks the center of the road. So yeah. From all the planning processes that you have learned, here's an example for the A1 autonomous vehicle by Hanyang University for the autonomous vehicle competition 2012 organized by Hyundai. So for this competition, you are tasked to travel along this dirt road. And this A1 has two different motion planners depending on the situation. So the first one is a road model-based path planner, which is used for structured roads. This motion planner is actually the conformal lattice planner that I previously mentioned. So initially, you model the center of the road using cubic splines. So now you will have the S here, and then we can formulate the path into finite frame coordinates. So in this case, yeah, the path candidates are generated based on the curvilinear coordinate system. Second. So the planner will generate the path towards this segment as the goal, for example, maybe SF, and then generates multiple path candidates. So path selection for A1 is based on three main components, which is the safety cost, smoothness cost, and consistency cost. Here, the cost is used together for the objective function. Safety, of course, is collision check, no collision. Then smoothness means the smoothness of the path, and consistency is how the path, how much the path diverges from the previous planning time step. So here is the collision check. So the path only uses path that has C equals to 0, which means no collision. Here is the smoothness path. So among the generated path, these are smoother, so these are preferred. Then consistency, this is the previous time step plan that it used. So you want to have the curve that is close to this previous curve in order for the trajectory to be smooth. Then combining all three, you will have this as your selected trajectory. So here's their demonstration. This is when there is no vehicle. Then you will have a slow-moving vehicle, and this is the multiple generated path candidates. And the blue line is the best path that it selects. So this is how it performs an overtake. The second motion planner used is for unstructured roads. In this case, when you don't have road map data. So the perception map is converted into an obstacle grid map. So here is your real diagram, and it's converted into this grid. And these black blocks represent the obstacle. Then, based on the grid map planning is then done in two stages. The graph expansion, which extends the graph based on the vehicle kinematic model. So using the kinematic model, you extend the graphs into nodes here. And this is the generated node. And then you construct the path that selects a safe and efficient path. So you construct many possible paths from the graph. And based on and then you combine, this process combines grid representation with kinematic lattice planning. So the path selection is based on the cost of the vertices of the graph. So firstly, the collision-free paths are selected. So you ignore nodes that is within the obstacle. And then the path cost that is considered are paths that depends on the proximity of the obstacle, which is based on risk. Then the accumulated distance in order to obtain the shortest path from the starting vertex to the jth vertex, and then the equilibrium distance between the goal and the jth vertex. So to summarize, it will select the shortest path towards the goal that avoids the vehicle. So here will be, for example, this node will be the lowest cost node with respect to the goal, and this node will be selected. And this is the final result. Here's their demonstration. So for structured roads, initially, they used that conformal lattice planner earlier. And then once it reached a road which have no road map data, it switches to the graph-based planner earlier. And then it converts back to the conformal lattice planner. Next is the velocity profile generation. So for velocity profile generation, the main points are the reference speed tracking, velocity smoothness, dynamic obstacles, acceleration limits, as well as the solution profile. So these are the things that will be covered for this velocity profile generation. So the goal of velocity profile generation is that given a safe path to the environment, a velocity profile governs the motion along the path. So this will determine what is the speed of the vehicle when it moves along the path that you generated from the local path planner. So things to consider for the velocity profile plan generation is that you need to execute the behaviors. You must follow the behaviors dictated by the behavior planner. And you also need to manage interactions between dynamic objects, and then observe lateral and longitudinal acceleration limits defined by vehicle dynamics. So for the behavior planner reference velocity, this is when you require the speed of the vehicle to track some reference speed. So here, usually the reference speed is the cruising speed along the vehicle. So, well, you also need to compute the reference velocity you need. It's based on the situation. For example, yeah, you can use the speed limit of the road as a starting point. And then the behavioral planner maneuver will also influence the reference velocity. For example, a stopping maneuver requires us to stop. So in this case, your reference velocity is usually set to 0 or near to 0. And for speed tracking, one way to implement it is by using a quadratic loss, where you penalize deviations from the reference velocity. Another way is to use the hinge loss, where you only penalize it when it exceeds the speed limit. So in this case, if the difference is less than 1, this loss will be larger than this loss. Then another thing to consider for velocity profile is to analyze jerk. Here, jerk is the third order derivative. And here's an example of when you don't penalize jerk. Here, the car starts immediately, but then you have this jump in acceleration and this spike in jerk, which is generally uncomfortable for the riders. Here, if you have the jerk penalty, you will have a smoother velocity profile and much less jerk that will be experienced. Then the third part that you need to consider dynamic obstacles. So usually in driving scenarios, the lead vehicle or the lead dynamic objects will dictate our speed so that we don't have any collisions with them. And one important metric for this is the time to collision, which is based on the velocity of the lead vehicle and the ego vehicle. So the lower the TTC means the more inevitable it becomes for the ego vehicle to collide with the lead vehicle. So ideally, you want to reach the red point at the lead vehicle speed to ensure that there is no collision. Next are the acceleration limits. But first recall the vehicle dynamics or the friction ellipse profile, which denote the maximum magnitude of tire forces before stability loss or before you lose control of your vehicle. So this is the friction ellipse. So this this limit is generally it's a useful limit, but it's generally like the maximum upper boundary of your acceleration that should be allowed. And however, for common implementations, you usually want to constrain the acceleration even further for more comfort. So this becomes the comfort rectangle range, which is here. So this is generally the comfortable range that you should have for your acceleration. And this is the maximum allowable. So friction limits and comfort restrict the lateral acceleration. Lateral acceleration is a function of instantaneous turning radius of path and velocity. So you can express the lateral acceleration in terms of this, the radius of the path and the velocity. And ideally, you would want it be below some max value. The radius of the path is related to the instantaneous curvature, or basically is an inverse of the curvature. And we can substitute that into the equation to obtain this velocity constraint, where now we will have a constraint that the square of the velocity must not exceed this formula. So since the lead dynamic obstacles regulate our speed to prevent collisions, the time to collision is an important metric to preserve when driving with lead vehicles. This is a summary of the velocity constraints. And we need to reach the red point at lead vehicle speed to ensure that there is no collision. So velocities are generally generated using profiles. A simple the simplest profile is the linear ramp profile, where we will have the initial velocity and our desired velocity. So now with this, we use the total arc length of our path and our initial and final desired speed to generate this linear ramp profile. So this will be the speed that the vehicle will follow when traversing through the path. Using the linear ramp acceleration, using the linear ramp profile, we can calculate acceleration using initial and final velocity as well as the path arc length. But we also need to be sure that the acceleration values don't exceed the earlier comfort rectangle. So if we clamp our acceleration, we can recompute the final velocity using this. We can recompute the final velocity using the clamped acceleration of A. So if this is the acceleration formulation, so we can use this to limit the acceleration in order to follow the comfort rectangle. Then for any given acceleration, we can compute the velocity at each point by using the accumulated arc length SI up to that point. So we have our acceleration that we want, and then we can calculate VFI from our initial position SI. So here we want the vehicle to be at VF1 at this stage of the plan and VF2 at this stage, for example. Next is the next example for the trapezoidal, for the velocity profile is the trapezoidal profile, usually represented by an acceleration or deceleration, and then some constant velocity, and then another acceleration or deceleration. So, yeah, in this case, the car decelerates to a, in this example, the car decelerates to a slower speed before stopping, and this is useful for stop sign scenarios. And the deceleration of this profile, similarly with the linear ramp profile, you need to choose it in order to comply with the comfort rectangle for maximum passenger comfort. So the first segment of this profile, we determine the distance required to reach the transit velocity Vt using a gentle deceleration A0. Once we have that, we can then recompute the linear deceleration for all points up to the point of reaching transit speed. So we determine Vt first and the A0, and then we can have the arc length that the first segment arc length. Using also, you can get the VFI using this formula. Then we can also repeat a similar process for the third segment, where we want to reach a stop from Vt using a gentle deceleration A0. So first we need to find the point of initial deceleration as B, or how long we want to travel at VT. The points in between first and third segments have constant velocity. Because of this, we will have constant velocity here. And then we can have a smooth deceleration towards 0. So bringing it all together, we will have our full velocity profile expressed in this form, considering 3 segments. So calculating the VFI, or the velocity along the points of the path, we can use this formula using these conditions. I think that's all for this lecture. To summarize, motion planning for autonomous driving is a highly structured planning problem, and we can decompose the task to exploit domain knowledge, such as lanes or dynamic vehicles. And then we also covered mission, behavior, and local planning decomposition. And local planning through variational methods leads to smooth plans that satisfy many constraints and minimize multiple objectives. And yeah, that's all for this lecture. And yeah, I think you also note that homework 3 is out. And question 3 for homework 3 includes, one second.